Now that we have our Docker image ready to be used, let's discuss our options for deploying containerized applications, and there are several options available. You could use Docker Swarm, for instance, or we could use Amazon ECS, which is Amazon's own container orchestration service, or Kubernetes. It seems to me that Kubernetes is considered the best tool so far, so that's what we are going to be using in this video series. All the major cloud providers have some kind of managed Kubernetes service that we could use. There is JKS from Google, there is AKS from Azure, and there is EKS, which is from Amazon. But we are going to be using DigitalOcean's Kubernetes service. It's by far the simplest and cheapest. And this is not a series on setting up a Kubernetes cluster, so we can keep it simple. Kubernetes is a container orchestration tool. We need such tools when we are deploying our applications to a multi-server environment, to what we call a cluster. Let's go ahead and create our first cluster. I have already created an account on DigitalOcean, and if we see in the Manage tab here on the sidebar, we go to Kubernetes and then we hit Create. We can then select a region, and for this video series I'm going to be using San Francisco 2. Feel free to choose the closest one to you. Then we need at least one pool of servers. By default it comes with 3 nodes, which means 3 servers, and we pay $10 a month per node. So let's reduce that price. When we do that, it shows a warning that describes that it requires at least 2 nodes to prevent downtime during upgrades or maintenance. If you're running a real production environment, it's highly recommended that you use multiple servers. For now, let's play cheap. Then you can choose the cluster name. I'll leave the name as is, cause YOLO. This will create a Kubernetes cluster with 1 node. As of now, DigitalOcean is not charging us for the Kubernetes master instance, so we are only paying for the nodes inside our cluster pools, which are droplets in DigitalOcean. While the cluster is provisioning, let's download and set up the CLI tools we are going to use to talk to the cluster. We'll need kubectl and doctl, which is DigitalOcean's own command line tool. You can go ahead to the official documentation on setting it up and follow the instructions there. It's usually a binary that you download and give it execute permission, and then you can use it on your terminal. I have already downloaded them here, so I'm not going to be doing that in the video. While the cluster is provisioning, let's connect our tool to DigitalOcean. And for that, we are going to need an API token. So go to the sidebar under Account, API, and create an access token. Give it a descriptive name. This is our token. We can copy it and use it in our terminal. So we are going to be authenticating our doctl tool, which we can do space doctl. Make sure you precede the command with a space so it doesn't get recorded in your terminal session history with the actual token. And that's done. Let's see if our cluster is ready. Looks like it's not. Let's wait a bit. Now that our cluster is ready, let's go back to our terminal and list our Kubernetes clusters. We can see our cluster here. Next, we are going to configure our kubectl to point to that cluster. My terminal already says that we are connected to our cluster, so we can test this out and run kubectl get nodes. This should list the only node in our pool. So this means that our kubectl tool is connecting to our cluster. Now that we are talking with our Kubernetes cluster, it's time for a short intro. We have been talking about containers, but in Kubernetes the smallest unit of work is called a pod. A pod consists of one or many containers. In a pod, containers will share the same network namespace. This means that containers from the same pod can talk to each other using localhost. Remember when we changed our Ngx site configuration to point to 127.0.0.1 instead of using the service name from Docker Compose? That's why. A pod is a very rudimentary abstraction. It doesn't provide much for us out of the box. We would have to terminate our pods and spin up new ones manually if we wanted to release a new version of our application. That's painful when you have to do it multiple times. That's why Kubernetes provides other objects that we can use, which are much smarter abstractions. Oh yeah, a pod is one kind of Kubernetes object. There are many available kinds, and each with their own particular use cases. Make sure you check out the official documentation to know more about the different kinds available. In our case, we are going to be interacting with a deployment object. The deployment will handle many things for us, such as making sure we always have a desired amount of pods running all times. So if one of the pods crashes, the deployment will notice that and spin up a new one to replace the faulty one. Well, actually that's a replication controller, but the deployment uses that under the hood, so we don't have to worry about it. It will also operate a rollout release when there is a newer version of the application available. There are many possible deployment strategies we could adopt when using Kubernetes. Some of them would require some manual work, like the blue-green deployment strategy or a canary release. But Kubernetes comes with other automated options we can use, such as the rolling update deployment and fixed deployment. The difference between these two is that rolling update deployments will terminate the pods of old images versions while it creates new ones for the new image version. That means we'll have two versions of our applications running at the same time for a short window. If you don't want that, you can use the fixed deployment strategy. When it comes to interacting with pods inside the same cluster, we usually don't point them to each other. We use another abstraction Kubernetes provides, which is called a service object. A service in Kubernetes is like a load balancer and a service discovery tool for our pods. Instead of pointing the pods to each other, we point them to the service, and the service will then forward the request to a set of pods. There are other types of objects, but that's enough for now. Let's play with our Kubernetes cluster for a bit. Let's create an Ngx pod there. And we can do that by running kubectl run, specify the name of the pod, which in this case I'm gonna call hello world Ngx. And then we can specify the image that we are going to use, which is Ngx version 117. And then we specify the port that we are exposing. We see a deprecated warning, but that's okay for now. We can see the status of our pods by running kubectl get pods. To be able to respond to external requests or inbound HTTP requests from our Ngx pod, we need to create a service. There are a few types of service we can create, but for now we are going to be using a service of type load balancer. The cloud provider, in this case DigitalOcean, will see that we want to create a load balancer, and guess what? It will create an actual load balancer for us. It's not free though. So you can imagine that if you have multiple applications in the cluster that respond to external HTTP requests, that price adds up. There is a way to reuse a single load balancer for our applications in our cluster, but I'll leave that for the next video. If you're curious, I have an old video where I do a similar hands-on process. We can create our example service running kubectl create service. I'm abbreviating service here with SVC. You can either use service or you can use the short version for SVC. And then we specify the type, which, as I said, it's a load balancer. Then we give it a name. I'm gonna call it Hello World LBSVC. And then we specify the receiving port and where it's going to send requests to. If we now go to networking, load balancers, we should see a new load balancer being provisioned. If we wait a few seconds, we'll get a public IP that we can point our domains to. We can also check the status using kubectl get service, just like we did with the pods. The external IP says pending here, but it will be updated as soon as it's provisioned. If we try to open it in the browser, we get nothing. That's because we haven't told our service which labels to watch. Labels are a very important concept in Kubernetes. We can use them to glue many things together. Remember that. For now, let's manually edit our service selector criteria. First, we need to know the labels our pods are using. You can do that by running kubectl get pods, get our pod name, and then run kubectl describe and specify the pod that we want to get more information about. You see an output here, and one of the items is actually the labels. So there are two labels being used. Pod template hash, which seems to be unique to this pod, and we don't want that. We want something that's more general. So we can use this run label. I'm gonna copy that, and then I'm gonna run kubectl get service. And now I can run kubectl edit and specify the service that I want to change. This will open up my editor and I can see the object manifest for the service. Here under specification, we can see a selector criteria. These are the labels that this service will watch out. We can change this to use the label that we copied. If we save that, Kubernetes will pick up the change and apply to the service. Now if we go to the browser and reload, try again because it might take some time to propagate, and then we can see the welcome page from Ngx. This means that our load balancer is sending the request to the service. The service is then forwarding that request to our pod, which is how we can see the Ngx response here. This is fun and all, but I'm not happy with this. So far, we have been manually running commands and editing live resources on Kubernetes. That's good for prototyping and poking around, but not very maintainable if you ask me. In other words, we have been executing commands in a very imperative way. Kubernetes allows us to do it in a more declarative fashion. Instead of manually running pods and creating services using kubectl, we can write down our desired object manifest and point Kubernetes to that definition. Kubernetes will then make the changes in the cluster for us to accomplish our goals. Let's delete the stuff that Kubernetes created for us. And try that approach. If we run Kubernetes get all, we can see all different types of objects Kubernetes created for us. And here's a deployment. So it turns out that when we run kubectl run, Kubernetes is smart enough to wrap that pod definition in a deployment for us. We can go ahead and run kubectl delete and specify that name. Now if we run kubectl get all again, we should only see the service. This is our service, so let's get rid of that as well. This means that our load balancer is gone. If we refresh this page, you should see that it's gone now. Let's create our objects manifest now. I'm going to my code directory and I'm going to create a Kubernetes demo folder. And I'm going to open it. Now I'm gonna create the manifest file for our Ngx deployment. And in this file, I'm gonna paste the code that we are going to use. So as you can see here, we are specifying a deployment kind of object. In the metadata, we are specifying the name of that object. Under spec, we are saying how many replicas of this pod we want and the selector criteria. Remember that I mentioned that labels are a very important concept in Kubernetes. Well, that's being used here as well. So our deployment is using this selector criteria to match the labels. So that's how it knows how many pods are running, and that's how it can spin up or terminate pods if we change this replicas count. Here we have a template. This template definition is what each pod is going to be using. Here we specify the metadata, which are the labels that our pods are going to be using, and this matches with the selector criteria for our deployment. Under spec, we specify the containers that are going to be running in our pod, which in this case is just Ngx, and the port is 80. We use a restart policy of always. Let's save that and go back to our terminal. We can see the file here, and now let's tell Kubernetes to apply this manifest to our cluster. We can use kubectl apply for that. And we specify the file that we are going to apply. Kubernetes created our pods for us, so we can go ahead and run kubectl get pods. Now we see the 3 pods are running. Now let's create our service manifest. Go back to Vim and create a new file called ngx service.yaml. And in that file, I'm gonna paste the code that we are going to discuss. So here I'm creating a service kind, and on the metadata I'm giving this service a name. Under spec, I'm specifying the ports rules. So I'm saying that any inbound requests sent to port 80 are going to be targeted to port 80 on the pods that match with the selector criteria. I'm giving this port rule a name so we can refer that later on. Also, here's where I specify that this service is of type load balancer. So when we try to create this service, DigitalOcean can act upon it and create the actual load balancer for us. Let's save it and try it. Now we see our service manifest here, and we can apply that to our cluster. We can either specify the file or we can specify the folder. In this case, I'm going to specify the folder so we can see a different output. You see here that Kubernetes detected both manifests, and the deployment one, it's unchanged, so nothing will happen in our cluster, but the service was created. In the background, you already saw that the load balancer popped up. So we can see our service status by running kubectl get service again. Let's wait a bit on the load balancer to provision. Now that that is done, let's try it in the browser. Let's copy it and open it in the browser. And we see the Ngx welcome screen again. So from now on, we would only have to change our Ngx deploy image, updating the image version name to a newer version and applying that to the Kubernetes cluster with this. And Kubernetes would roll out the new version to the cluster. And with that, we are ready to deploy our application to Kubernetes. But before we end the video, let's talk a bit about persistence. Our application will need both MySQL and Redis for running. Kubernetes and containers in general are very good for running stateless applications. But when it comes to stateful applications like databases, it's a bit of a challenge. In Kubernetes, we have a stateful set object kind, and we could use that in this series as they are production ready. However, I'm not used to running those in production. I prefer to pay a bit more on a hosted solution for the stateful services my application use. Usually, the cloud providers make it really easy to scale up and down these stateful services, which makes my life easier as well. If instead we were maintaining those services ourselves, we would be in charge of scaling replication and as well as dealing with downtime and crashes which may happen. With that being said, stateful sets are a wonderful way to run stateful services in our cluster. They work well, just require a bit more knowledge on how to operate them. For that reason, I prefer to use a dedicated or hosted solution for those. However, we are going to be running Redis as a stateful set for the sake of demonstration. For now, let's finish up the video by creating the database. So we can go back to the dashboard on the database, select create, then we can choose MySQL, which is my preferred database of choice. Then you can pick a size. I'm gonna pick $15 a month, the cheapest one. And then I'm gonna run it in San Francisco region, closer to my server. Feel free to give it a name. I'm gonna leave it as is. Now we can finish up by provisioning some security for our database cluster. We are adding some trusted sources here, which tells the cluster that it's okay to accept connections from these parties. So we are going to select our Kubernetes cluster and hit allow. It's important to notice that we are not going cheap here. So we are paying $15 a month for the database cluster, but we can reuse that for different applications depending on our needs. And we are also paying $10 a month for the droplet running in our pool. And we also have a $10 a month load balancer. So that's $35. In the next video, we are going to see how we can actually reuse this. But both the database and the load balancer, they can be reused across many applications. And you can also deploy many applications to the same node pool. So you could potentially run multiple applications in a reduced amount of servers. Now we are actually done. In the next video, we are going to be creating a database and a user for our cluster, as well as deploying our application to the cluster and dealing with migrations and all that. So I hope you liked it and see you on the next video.